Hello students and welcome to this lecture, and in this lecture we're going to be hitting up on sections 8 and 9 of chapter 6. So far in chapter 6 really what we've covered is this idea of SN2 reactivity. Alright, so let's review that really quick. Substitution, nucleophilic, bimolecular. Alright, so we have some sort of nucleophile. Here we'll just make it OH minus. Has a negative charge. It's really going to come in and it's going to be looking for something such as a chlorine attached to a carbon. Why is that important? Remembering, of course, that the carbon, when it's attached to a chlorine, a halogen, is partially positive. Chlorine is partially negative. And that, again, the nucleophile looking for a nucleus, looking for something that's more positive charged, comes in, is attracted to that group, and then this second arrow occurs where the chlorine breaks apart and end up forming a new product where the OH has substituted as a nucleophile for the chlorine and now is attached to the carbon. So remember that looks like this now. Remember, we also get what's called inversion of configuration. That is, this guy flips around. We get something like that, plus the Cl that's over here off to the side. All right, and so this goes through this. So inversion of configuration, we might also say that this is a concerted reaction. That's one of the things that we use, concerted, in the sense that this arrow comes in and this leaves at the same time. And that also, the bimolecular, this is second order, that the concentration of the OH and of this, the substrate, both of those are important for this reaction. All right, so this is the SN2 mechanism. We're basically spending the whole chapter studying that, and it's one of our first in-depth mechanisms. All right, so so a couple of things. We talked about the leaving group and the importance of it. In this particular section, we're going to talk about the nucleophile and think about that and how important the nucleophile is in determining the rate of this. All right, so the ability of a substance, say OH minus or Cl minus or iodine, to act as a nucleophile is referred to as its nucleophilicity. All right, so it's the nucleophilicity, the ability of something to act as a nucleophile. That depends on a couple of things. One of them, charge, whether it's charged or not. So it has typically a negative charge. It's going to make it more of a better nucleophile as opposed to something that's neutral. How good of a base it is. The solvent, how well the solvent actually traps the nucleophile. So this one is dependent really upon the solvent. Size often has an ability to talk about polarizability, so how much the electrons can be polarized, and then also the nature of the substituents, that is the groups that are coming off, that is the R groups that are coming off that central carbon, and how branched it is. A couple of experiments to help us understand how important the charge is for the nucleophilicity, right? The ability of something to act as a nucleophile. In science, we often want to look at experiments to figure things out and to look at overall data. We've done this in lab with the SM1, SN2. We compare various things. So let's compare a couple of experiments. Number one, this experiment is where we have a substrate, which here is just chloromethane. Right, so a methyl group with just one chloro, and it's reacted with either hydroxide, an oxygen with a negative charge, or water, so an oxygen that has two hydrogens. Oxygen, hydrogen, negative one charge. Oxygen, two hydrogens, no charge. We allow that to go and basically look at how fast it occurs. Look at how fast, let's say, this occurs, and we might look at that by precipitation of chlorine, as we did in the lab, or just somehow measure that. What we find is that the oxygen that's charged is very fast. The one that is uncharged is very slow. All right, so notice that really we haven't changed very much. We have the same substrate in both cases. We have the same element, oxygen, that's being part of the nucleophile, attached to hydrogens, and we're really getting the same product primarily. I mean, it's got an extra hydrogen, and this is the leaving group's the same. But what has changed, of course, is the negative charge. All right, so this one's negative, this one's not. Negative fast, neutral charge very slow. If we do almost the same experiment, experiment number 2, where again, substrate with the leaving group chlorate are the same, we have the nitrogen that's charged, nitrogen that's neutral. We effectively get the same product with chlorine going away. And what we find out is this one's very fast and this one's slower. The difference, once again, is this negative charge. All right, so this really tells us and teaches us that this negative charge makes something a better nucleophile. That is, its nucleophilicity increases as we add a nuclear charge. All right, so this is sort of formally written out the overall conclusion, comparing nucleophiles. All right, so again, these are the nucleophiles, having the same reactive atom, oxygen here, nitrogen there. The species with the negative charge is the more powerful nucleophile. All right, so and that's we get that. And again, if we actually did the reaction, you would see this in the lab. You would actually see this well. All right, so and here it says a base is always more nucleophilic is the word that we want to use than its conjugate acid. All right, so what we mean by that is that this is the base, this is its conjugate acid, right? So this has one more proton, and so water losing a proton would be acting as an acid to deliver this. NH3 would act as an acid, delivering a proton to something else, becoming this. All right, so the negative charge does increase the nucleophilicity. The next property we want to look at is the nucleophilicity as it decreases to the right in the periodic table. Right, and so what we mean by that is that as we're looking at various atoms, as we go from, say, boron, the carbon, the nitrogen, the oxygen, the fluorine, that nucleophilicity, the ability to act as a nucleophile, decreases as we move to the right. So we can prove that if we, again, have a substrate with the same leaving group in two different experiments or two different trials in an experiment. We have nitrogen and oxygen, neutrally charged here with hydrogen, so similar groups that are attached to it. And again, notice where nitrogen is and oxygen, where they are in the periodic table. We run the reaction, again, get similar types of products, similar charge, leaving groups the same. Notice nitrogen is fast and oxygen is slow. Right, and so again, nitrogen, it's a little bit more to the left, is faster, and oxygen is slower, it's to the right. So oxygen has lower nucleophilicity based on this. These were neutrally charged. Let's take a look at really the same reaction with the substrate leaving group and nitrogen and oxygen, but in this case, they are negatively charged. You can get similar products, same leaving group. Again, noticing that nitrogen is very fast, oxygen slower, and again, we're just accounting for this negative charge. And so really we get the same result, is that nitrogen, which is a little bit further to the left, is a better nucleophile than oxygen, which is further to the right. So overall, we can say that nucleophilicity correlates with basicity. And as we proceed from the left to the right on the periodic table in a particular row, the nucleophilicity decreases. All right, and so again, if we can rank them, we know that nitrogen, its negatively charged, would be stronger than OH minus, and that would be, and oxygen with a negative charge actually would be stronger than a nitrogen with that's uncharged and the fluorine, and then we see here oxygen is really the worst nucleophile. Clearly, these are not the only nucleophiles, but these are common ones, and a way to help us understand how this nucleophilicity changes based on trends and sizes in the periodic table. All right, should basicity and nucleophilicity be correlated? All right, so that's sort of the question. Should they be correlated? And why might we ask this? We might remember that basicity is a thermodynamic property. And thermodynamic really deals with delta G, delta H, delta S. We talked about those. Remember, delta G is Gibbs free energy, and that spells if a process is spontaneous. Delta H, remember delta H deals with heat, and so delta G, delta H minus temperature times delta S, and S is entropy. All right, so that's what we mean when it's a thermodynamic property. One of the ways that we can also write delta G is equal to the negative RT ln of K, and this is the equilibrium constant K. All right, and so ultimately the larger the equilibrium constant, that is the larger that this concentration of the products are, that means the more negative, since there's a negative sign here, the more negative delta G is and the more spontaneous. All right, so basicity is really compared with how far this thing goes to completion. All right. On the other hand, nucleophilicity is a kinetic phenomenon, and that deals with lowercase k, and this is a rate, and it really deals with speed and really how fast these reactions go. All right, and so, and we hit upon this back earlier in the semester, but really in thermodynamics and kinetics are really two different ways to talk about reactions, and they really deal with two different ones. So, hence our question, should basicity and nucleophilicity be correlated? Because fundamentally, one's based on thermodynamics, the other one's based on speed. What we find is that despite this difference, this fundamental difference, that there is actually good correlation. If something's a good nucleophile, it's also a good base. Or if something's a good base, it's also a good nucleophile. And in this particular case where we have charge versus nucleophiles, neutral nucleophiles, along a row in a periodic table. All right, and so we generally see that once we're, again, on the same row, like the oxygen and nitrogen that we're talking about. All right, so just reminding us. One of the things that we also need to talk about is the importance of solvation and how it impacts nucleophilicity. Now, it might seem a little bit weird because when we started this section, we talked about the importance of various aspects of the nucleophile to impact its nucleophilicity. And the solvation is not about the nucleophile per se. However, what we do find is that the solvation does influence the nucleophile, the nucleophilicity, and the nucleophile in this. And depending on how well and how strongly the solvent holds on to the nucleophile. Another experiment where, again, we have the same substrate with leaving group. In this case, we're looking at oxygen and sulfur. They're both charged, both have methyl groups attached to them. Of course, remembering that right here in the periodic table, oxygen and sulfur are above one another. Above and below one another, oxygen's above, sulfur's below. We run this reaction, we get similar types of products. R group, oxygen R, sulfur R, same leaving group. What we find out is that oxygen is not very fast, but sulfur is. And we might expect that oxygen will be better because it's a better base. We learned a little bit about that. One of the things that we can see from this, and if from this experiment, if we ran other ones like with nitrogen and phosphorus and sulfur and selenium, is that nucleophilicity will increase down a column of the periodic table, which is the opposite predicted by the basicity of the nucleophiles. Because oxygen is a better base, we might think that it would react faster. And so it should be more reactive. Sulfur, however, we find out is less solvated, so it ends up being more reactive. So it's the better sort of the two, whereas oxygen, again, not that it doesn't react, but it's not that reactive. All right, and so why is this? Well, let's go on and talk about this just a little bit more. Solvation, and we'll see a little bit what I was talking about, it surrounds the solvent and sort of impedes it. All right, and so if we think about it like this, is that we might think about like sodium, positively charged, and if it's an methanol, like we just talked about. So here would be the carbon CH3OH, is that it's positively charged. Then what would happen, of course, is that this is positively charged, so it's going to be attracted to these negatively charged oxygens, and there's going to be a fair amount of solvation. That's for the positively charged sodium. If we look at fluorine, which is negatively charged, these methanol molecules would surround it, but actually the hydrogen, which are partially positive, they would be pointing at it, and so we'd say that the fluorine is more solvated. Compare the size of the fluorine with a relatively large iodine, and what we say is that because of this iodine's much larger, right, and it's not as densely charged, that there are actually going to be fewer solvation molecules which surround it. And so because there are fewer molecules that surround it, iodine's better able to move around, right? It doesn't have this like drag on it. Whereas fluorine has more of these that are surrounding it, dragging it, and not allowing it to move and act as a nucleophile. Because remember, to act as a nucleophile, it's got to be able to move and attack or be attracted to a carbon, partially positive a carbon. But in this case, it can't move as well as the iodine. All right, so the point is that the solutes, sodium, fluorine, iodine, they are surrounded by the solvent. In this case, it happens to be methanol, but it could just as well be water or something else. All right, so just summarize this. So basically, the solvation impedes the nucleophile by forming a shell of molecules around it. So this would be the shell. All of these ions have a shell around them, but it just that the shell around fluorine is thicker because it's smaller, more densely charged. Iodine's bigger, and so it's considerably larger than these molecules, and so they can't form it around it as well and hold on to it. And again, generally, as we saw, that smaller ions are more solvated than larger, so fluorine's more solvated than iodine, and so that's why iodine can actually act as a better nucleophile. One of the things that we need to think about when we start talking more about these solvents is whether they're protic or aprotic. All right, so protic solvents are those that have hydrogen bonding capacity. All right, so that would be something like OH or NH2, and we know that these can form hydrogen bonds. All right, and so we just saw CH3, OH, show up with a little bit more of its bond angle. And so then again, we can get these hydrogen bonds that can form, and that might be with something like even water. All right, so these are called protic. So they have protons, again, the hydrogen here, that are attached to either an oxygen or a nitrogen. Now you might say, what about these guys? Aren't those protons as well? They are hydrogens, but because they're attached to a carbon, remember those cannot form, these cannot form hydrogen bonds, so they don't form it. All right, whereas the ones that are attached to oxygen or nitrogen, oxygen here or nitrogen, those can form hydrogen bonds, and those are referred to as protic solvents. Aprotic solvents lack the polarized hydrogen, and they're often used in SN2 reactions. All right, so that would include something like acetone or the nitromethane, all right, which don't have those hydrogens attached to an oxygen here, here. And so these are often used in SN2 reactions because they don't hold on to the nucleophile as strongly and allows something like iodine to actually react. All right, so these are referred to as aprotic solvents. They don't have hydrogen attached to an oxygen or a nitrogen. All right, they do have hydrogens, but these are not attached to an oxygen or nitrogen, and so they're not considered protic, so they're referred to as aprotic. Let's look at a couple of animations to help understand this solvation. So for the first one, we're going to be looking at the role of methanol in this solvation and really reducing the nucleophilicity of OH minus. So we have methanol, which remember, again, just so we're drawing it out, methanol CH3O. Right, and so we see that, and so again, it can form a hydrogen bond, so this will be referred to as a polar protic. So it's both polar and it's protic, or it can form a hydrogen bond. And so in this case, what's going to happen is that the OH is going to react here with the CH3Cl, and the OH minus, of course, is going to be the nucleophile. This video, or the animation, and I'll start it here, is going to help illustrate how methanol here is holding on to OH minus, not allowing it to attack and be attracted to this CH3. Here's the Cl that's coming in. So eventually, the OH does come in, it reacts through an SN2 mechanism, and the chlorine goes away. All right, so if you notice, what would happen, of course, is that just like chlorine, the methanol atoms are surrounding it. Because they have the ability to form hydrogen bonds, they are strongly attracted to things that are charged. Now, this isn't a true hydrogen bond, but the point is that their ability to hydrogen bond allows them to interact with other species such as Cl minus or OH minus more strongly. Now let's compare that with methanol with a different compound, and I'll pick a different one. And so this again is OH minus with CH3Cl, the same thing, but notice we have something known as DMF. Now, what is DMF? You might ask. Well, DMF is dimethyl formamide. I will draw it so you can see what it looks like. All right, and so again, it's dimethyl formamide. And so here's the dimethyl part, the two CH3 groups that are here. This is the amide part, dimethyl form. This is the formaldehyde amide. All right, and so again, you have this carbon double bonded oxygen with an H. If you had another H here, this would be formaldehyde. In this case, it's a form group, and this is amide because it's got a carbon double bonded oxygen nitrogen. This is an amide, and then we have these methyl groups. So notice again, we have hydrogens, but this is what we refer to as a polar. It's polarized again because of that carbon double bonded oxygen and the nitrogen, but it is aprotic, not protic, is what aprotic means. And so as a result, this one cannot form hydrogen bonds, but it's still a good solvent for SN2 reactions. And let's take a look at this animation to help us illustrate why. So again, we have these dimethyl formamids. They're around the OH minus. They're not holding onto it nearly as strongly. It can come in and attack this group, and then the chlorine goes away, all right, as the leaving group. But this one happened at a much faster pace. All right, but the point is, and the take-home lesson is that polar aprotic solvents, so polar aprotics, are good for SN2 reactions. All right, so they are good. So the SN2 reactions prefer this because, why? The solvent does not hold on to the nucleophile quite as strongly, sort of slowing it down. All right, and so again, it's imagine like you're trying to walk across like a big field, and there's lots of people, and you have to weave in and out. All right, and everybody's. But if it's less densely populated and there's not as much contact, you can walk across that field quicker. All right, and again, so this is about not the number of solvent molecules, but basically how fast they can progress. All right, and so polar aprotic solvents are favored for SN2. Let's do a couple of these, and so think about what are the solvent that I'm going to show you is protic or aprotic. So you give thumbs up or thumbs down. If we're in class, then I'd give the whole class give thumbs up or thumbs down, but just take a second. Is this protic or aprotic? Well, in this case, of course, this one is protic. It's water. How about this one? All right, so this one would be aprotic, right? Because this is the one that we just saw, dimethyl formamid. So again, it does not have a hydrogen that's attached to a nitrogen or an oxygen. Protic, right? So we have this guy right here, and that makes it protic. All right, protic again. We have this that's going on, so that can form a hydrogen bond. Aprotic here. Again, hydrogen's out here, but they're not attached to an oxygen or a nitrogen. All right, so those are the types of aprotic solvents that we saw in those last couple of slides, which would be important here. So aprotic solvents do not solvate the anionic nucleophiles well, and they result in increased nucleophilicity. All right, so again, table 6.6 helps to show this. So again, we have a couple of things that are protic and some that are aprotic. Or that's actually just one that looks like it's aprotic here. But in this case, we have 3 protic solvents. Notice their relative rate. All right, so 1 to 45, which is pretty big. Well, you compare it to 1.2 million for the aprotic. All right, and this is the NN-dimethyl formamid, which is what I just called it dimethyl formamid, but it's called NN-dimethyl formamid a little bit ago. So this one clearly, this kinetics, comparing to 3 other protic ones, all show that, again, aprotic are great. Again, thinking why? You have OH, NH, NH, all hydrogen bonding, so that would make them protic. At the beginning, we saw that polarizability of the nucleophile also changed or increased its nucleophilicity or nucleophilic power. All right, so again, the degree of nucleophilicity increases down the periodic table, and that's even for uncharged nucleophiles. All right, and that's because they actually are much larger, and that's because the solvent effects also are much weaker. All right, and so again, thinking fluorine, chlorine, bromine, and iodine. Iodine's to the bottom of that, it actually is more polarizable, and so it has a greater nucleophilic power. We can also see the same thing as that selenium more towards the bottom of the column than sulfur and oxygen. So selenium would be a redder nucleophile. Same thing with phosphorus and nitrogen. All right, so phosphorus is lower. And so again, these atoms that are lower are again larger, and they're actually can be more polarized. And here, if you're just comparing, say, iodine and fluorine that I talked about earlier, notice the lobe of the lobe of iodine. It's much larger than fluorine here. And so again, we can polarize it more. There's a bigger area for those electrons to be polarized. And again, towards sort of the carbon center. All right, so that's one of the things I have to think about, how polarized a particular atom can be. We also can talk about sterically hindered nucleophiles. All right, so how sterically hindered they can be. So in this case, we have, what do we mean by steric? Well, again, we've talked about steric hindrance and other things earlier in the semester. And so, again, nucleophiles having larger, bulky substituents are not as reactive as unhindered ones. So let's be clear. So this is one nucleophile, and it would be, it's not real clear, this would be unhindered. all right, because basically you have the oxygen and just this R group here. It's just one of them, and so it's unhindered. Whereas this guy, carbon, oxygen, but it has 3 other R groups around it, that would actually make this sterically hindered. And so as this oxygen, which has a negative charge, is trying to go in and sort of attack from the backside, all right, this bulk, the steric bulk, would actually end up slowing it down. And so again, the experiment is we have 2 substrates with the same leaving groups, same oxygen atom, just we've changed the hindrance. So not and very hindered get very similar products in terms of carbon, oxygen, carbon, carbon, oxygen, carbon. Lots more substituent here, and again, faster versus slower. So this one just proceeds much slower. So what we can say is that sterically hindered nucleophiles react more slowly. Oftentimes in a regular class I would say, all right, what makes it bulky? But I've already told you what the bulk is, and the bulk is ultimately just this R groups, these carbon groups that are surrounding it. Nucleophilic substitutions are also reversible, or they can be reversible. And we've used the halide ions, and with the exception of fluorine, they're actually both good nucleophiles and leaving groups. And when we see a reaction like this, we see the R group, iodine, which is the leaving group, chlorine coming in as the nucleophile, and just noticing, of course, that the arrow's bigger in this direction, this forward direction, smaller in the reverse. All right, and so that just means that the reaction is more favorable towards the product side. And again, noticing it happens in acetone, a good a polar aprotic solvent. And so we end up with the lithium iodine and this attached. And one thing about this is that the sodium halides, they dramatically decrease. So this sodium iodide is much more soluble than sodium bromide and sodium chloride. All right, so in the laboratory we actually use iodine as a nucleophile because it's actually more soluble, and these actually precipitate. And so in fact, let's take a look at that. Sodium chloride is virtually insoluble in acetone, and so it would form a sodium chloride solvent, a solid in the solvent. And so this is the type of experiment that we ran, where we would have this chloro group, iodine being added, and it comes in, again, an acetone, and we end up with this as a product, and this is an insoluble precipitate. So the down arrow means that it's insoluble. All right, and so this is one of the reasons that we ran the reactions as we did in the laboratory. And if you haven't seen the laboratory, just keep this in mind as you watch it. So this table just illustrates the point that we were making about the solubility and how the nucleophilicity changes. And again, thinking about the idea of how polarized they are, how good of bases these can be. All right, and so just notice as we sort of go down here, iodine ends up being a great nucleophile, which is why we use it as the nucleophile in some of the experiments in the laboratory, and some of these others that are here. All right, so we can see how good of nucleophiles they can be. Some of these are really strong, and then other ones of these are fairly weak. The last thing that we can talk about is that the nucleophilic substitutions, when they do substitute, they can actually change the stereochemistry between these substituents. So this is showing a cis 1-bromo-3-methyl. So cis means same side, the bromo group, and the CH3 are both sort of away, those wedges that are back. Iodine comes in. Again, remember the iodine is going to attack from backside to kick off the bromine, and over here the bromines here wedge out, and this is the hashed ones behind, and so it ends up with a trans. So we also have to think about that. So in this case, we're going from a cis to a trans species. And then overall, this was one of the reactions that we saw earlier, just in terms of the HS, the sulfur acting as the nucleophile, coming in, attacking this partially positive carbon, kicking off the bromine, and then getting that inversion of configuration. This is a great slide just to finish up with, to remind us of our mechanism. We need to know this mechanism of this coming in, this going away, leaving this. This helps us understand inversion of configuration, going from R to S. Also understanding that it's bimolecular. This and this are the things that are involved in the rate-limiting step. It is also one step, 2 arrows, but one step, and this works along. All right, so remember that this is the SN2 mechanism. All right, and that was really, this whole chapter was really about understanding the SN2 mechanism and how to make it react better, and what particular solvents, what particular substrates, and other things help to react, for it to react better, that is SN2 reactions.